In this video, we're finally going to do what we've been building up to in the last several lectures, actually plotting halo orbit trajectories. To plot such a trajectory, we need an initial state that we can numerically integrate using the nonlinear equations of motion. For the initial state, we need 6 parameters, xyz position and xyz velocity. Position is straightforward. We want to examine behavior around a Lagrange point, so obviously our position is somewhat close to the point. But what about velocity? Velocity is not straightforward. There's no intuitive way to look at this and figure out what the velocity needs to be in order for the trajectory to orbit the Lagrange point. This is why we did the stability analysis in the last lecture. Let's take a look at that. In the last lecture, we linearized the system and we got it to a form x dot equals ax. Now, when you have equations of this form and a is constant, you can write the solution to this sort of system in the following form, where lambda 1 through lambda 4 are the eigenvalues of the A matrix from the previous slide, eta 1 through 4 are the corresponding eigenvectors, and c 1 through 4 are constant scalar values that depend on the initial conditions. Now, what does this have to do with finding the initial conditions? So we know that lambda 1 and 2 represent stable and unstable modes of the system, and lambda 3 and 4 represent oscillatory modes. So what we can do is we can sort of invert this. Instead of using our initial conditions to find C1 through 4, we're actually going to kind of do half and half. We're going to state that C1 and C2 are going to be 0, because we don't want these terms showing up in our solution at all. We want our solution to only depend on the oscillatory modes. And we're going to fix our initial position. At that point, we're going to have our initial velocity and these C3 and C4 terms as unknowns, and so we'll have a system of 4 equations with 4 unknowns. So let's write this in vector form. And actually, first what I'm going to do is I'm going to explicitly write out what x of 0 looks like, because we know that e to the 0 is 1, so our initial conditions are simply c3 eta 3 plus c4 eta 4. Remember that these are vectors. So if we write it out in a vector format, we'll have x naught, y naught, x dot naught, and y dot naught. And that's going to be equal to c3 eta 3 plus c4 eta 4. And we can also write that in a matrix form. So this is actually a 4 by 2 matrix, and this is 2 by 1, because remember, these are vectors. So here, like I said, we have a system of 4 equations, and we have 4 unknowns. These are our unknowns, the initial velocity and the C3 and C4 values. The initial position we're going to dictate. We're going to say that we want to start, say, a kilometer away from the Lagrange point. And the eigenvectors, we're going to find those in a minute. But first, let's do a little bit of algebra to rearrange this stuff, because we can't solve this system as it is. I mean, for one thing, our unknowns are on both sides, right? Usually we want a system that's of the form ax equals b, where x is our unknowns. There's a number of different ways to rearrange these things and solve for the quantities we're interested in. What I'm going to do is I'm going to write out the equations and show how we can rearrange them to get what we want. So if we write this out instead of matrix form, if we just write these out as equations, we're going to see that x naught is equal to c3 times eta 3 1 plus c4 times eta 4 1. So that's the first component of the eigenvector associated with lambda 3 and the first component of the eigenvector associated with lambda 4. So the way I'm going to solve this is I'm going to take these first 2 equations and I'm going to rearrange them so that we can write C3 and C4 in terms of x naught and y naught, and then we'll plug them back into here so that we'll have x dot, the initial velocity, and y dot naught, the initial y velocity, in terms of the initial position. So to do that, let's put this one back into a matrix form. So for that we can say, and so we want to invert this matrix over here. Now the inverse of a 2 by 2 matrix is pretty straightforward. So here. So the inverse of a 2-by matrix is simply 1 over its determinant times the main diagonal flipped and the negative of the off-diagonal terms. So what that means here is we're going to get 1 over, so we know that this multiplied by x naught, y naught is going to give us C3 and C4. I'm going to make one more note here about this two set of equations. So these can be written as, from here, I'm going to take an aside and we're actually going to find the eigenvectors, because some of these eigenvectors are going to simplify and they're going to make our math a lot easier if we actually find the eigenvectors first. So let's go ahead and do that, and we're basically just going to put a pin in this and come back to it once we found the eigenvectors. So an eigenvector is a solution to an equation of the form ax equals lambda x, where lambda is an eigenvalue. Actually, let's use eta. And so we can rewrite this by saying that this is going to be a minus lambda I times eta equals 0. Now, usually when you learn about eigenvectors, you compute this matrix and then you sort of visually inspect it for how linear combinations of the different columns are going to give you 0. Doing that in this case would be a nightmare, because look at the eigenvalues. I mean, this is what our eigenvalues look like. This isn't even what the eigenvalues look like. They look like the square root of this, so it's a huge mess. Fortunately, we can do a sort of a trick here, where we're actually going to leave lambda as a symbol and go through and try to find the eigenvectors in terms of lambda the symbol, and then we can plug in lambda later on. So to do that, let's write out this matrix, A minus lambda I. So A was our matrix from the previous slides where we did the linearization. So if we subtract minus lambda I, you see that the main diagonal is just going to be negative lambda and everything else is going to stay the same. So you know that when we multiply this matrix by a general eigenvector, and here I'm going to use this notation where I'm going to say eta x1, eta x2, eta x3, eta x4, where this is some eigenvector. And it's going to correspond to whatever eigenvalue we choose here, but we know that this is going to equal 0. So now we have a system of equations that we can solve symbolically. Like you can see that these are all fairly straightforward. So for example, the first equation just shows us that negative lambda times eta x1 plus eta x3 equal to 0. So let's go ahead and write that down. The second equation tells us something similar, negative lambda eta x2. And let's go ahead and write down the last equation as well. So I want to solve for things in terms of eta x1. We can pick any one of these values to solve for, but I'm just going to pick eta x1. So I know that I can write eta x3 as a function of eta x1. That one's pretty easy. Let's go ahead and rewrite this equation in terms of eta x1 and eta x2, because that should be pretty straightforward. So we know that eta x3 is equal to lambda eta x1. So we can write this as, and let's also use the fact that eta x4 is equal to lambda eta x2. And when we rewrite this one, we're going to see, and then we remember that we're working on the collinear Lagrange points, so fxy goes to 0. So what I'd like to do is I'd like to use the first equation to solve for eta x2 in terms of eta x1. Then we'll have everything in terms of eta x1, because we have a formula for eta x4 in terms of eta x2. So let's do that. So if we take this first equation, we'll notice that 2 lambda eta x2 is equal to, I'm going to go ahead and distribute the negative here, so it's going to be lambda squared minus fxx by eta x1. So eta x2 is equal to lambda squared minus fxx eta x1 over 2 lambda. So now we can rewrite this eigenvector as follows. It's going to be equal to eta x1 up here, and then eta x2 is going to be lambda squared minus fxx by eta x1 over 2 lambda. And then we have eta x3, which is equal to lambda eta x1, and then eta x4, which is just lambda times eta x2, so that lambda in the denominator is going to go away, so we're going to end up with lambda squared minus fxx by eta x1 over 2. And notice that we can pull this eta x1 term out of here, so that's going to be 1, and then lambda squared minus fxx over 2 lambda, lambda squared minus fxx over 2 times eta x1. Well, eta x1 is essentially just an arbitrary constant, because we know that any eigenvector that satisfies this equation, any scalar times that eigenvector is going to satisfy this equation as well. So we can just decide that it's going to be 1. So now we're only interested in eigenvectors 3 and 4, so let's take a look at what those are going to be. Eta 3 corresponds to lambda 3. And here I'm going to note lambda squared is equal to what we referred to as big lambda in the previous lecture. So we're going to have 1, and that's going to be big lambda 2 minus fxx over 2 lambda 3. Lambda 3, and again we have big lambda 2 minus fxx over 2. And then eta 4. Now here, this corresponds to lambda 4, but let's note that lambda 4 is nothing but negative lambda 3. So we can rewrite this in terms of lambda 3. So that's going to be 1 over big lambda 2 minus fxx over negative 2 lambda 3, negative lambda 3, and then because this one doesn't have lambda appearing directly, only in terms of big lambda, it's going to be the same. Lambda 2 minus fxx over 2. So, okay, so now we have that. So now that we have that, notice how things are going to simplify a little bit over here. So eta 4,1 and eta 3,1, those are both just 1, and they're being multiplied through here as well. Eta 4,2 and eta 3,2, well, those are negative of each other, so that's just eta 4,2 in there. So let's go ahead and return to this one. And let's just note here so we can make a note here so we can maintain the flow. So now we can write this guy as 1 over, so we noted that eta 3,1 and eta 4,1 are both 1. So it's going to be eta 4,2 minus eta 3,2. And then here, eta 4,2 negative eta 3,2, and then minus 1 and 1. And then that's equal to, or that's multiplied by x naught, y naught, to give us C3 and C4. And let's note that eta 4,2 is equal to negative eta 3,2. So I want to write everything here in terms of eta 4,2. So we know that this here is going to be 1 over eta 4,2. And then this is going to be eta 4,2 appearing here twice. So let's bring this constant into this matrix. And it's going to give us essentially 1/2, 1/2. And here we're going to have negative 1 over 2 eta 4,2 and 1 over 2 eta 4,2. I guess we could have cut the 1/2 outside to make things a little bit nicer, but that's fine. There we go. we'll draw an arrow there to make sure that the equal sign is correctly interpreted without the context of the voice. So then, yeah, multiplied by x naught, y naught equals c3. So let's go ahead and plug that into here. Now a to 3, that's just lambda. A to 4, 3, that's negative lambda. So that equation is going to be a little bit simplified. So let's take a look. We're going to have, we'll pull the 1/2 out here. So it's essentially what we're going to do is we're going to plug this equation into here. So we're going to have a to 3, 3, which is lambda 3. And then we have negative lambda 3. And then we have, I'm actually going to leave these two as the same item, a to 3, 4, a to 3, 4, just so I don't have to write the whole thing. And then that's going to be 1, 1, and then negative 1 over a to 4, 2, and 1 over a to 4, 2. And then, yes, multiplied by x naught, y naught. That's going to give us our initial velocities. So let's see if we can try to squeeze everything into a single page here. If we multiply this one first, if we multiply these two matrices first, then what we're going to get is 1/2 by a matrix. So if this is 1 and 1, then this matrix is going to be 0 and 2, a to 3, 4. And then if this is negative 1 over a to 4, 2, and this is 1 over a to 4, 2, then I know that this is going to be negative 2 lambda 3 over a to 4, 2. 3 over a to 4, 2. And then the one on the bottom is going to be 0. And then lastly, let's see, the 2, that's going to go away from here. So essentially what we see is that, but yeah, now we have these nice, neat equations for the initial velocity in terms of the initial position. I should note I ignored z in this case because they're decoupled, and also we're just focusing on the planar case for the moment. So now let's head on over into Python, and I have already coded these up in a library that I've published called CR3BP, in order to save us the trouble of having to code all this stuff up. So we're gonna use that library, and we're gonna go ahead and pick some initial conditions and make some plots and see what things look like. Okay, so like I said, I've coded up the equations of motion and the initial velocity in Python, among a couple other things. So I'm going to briefly show you what that library looks like, and then we're going to go ahead and use it to start plotting some trajectories. So here is the library. It's available on PyPy, so you can just install it with pip install. And here's what it looks like. It's pretty tiny so far. It's a couple hundred lines. The main aspect of it is this system data class, which takes in two masses, a primary and a secondary, and a distance. And then it has a whole bunch of properties. So it'll have mu, it'll have theta dot, the total mass. Has a conversion vector as well as a function for converting the state, and it also has values for all of the Lagrange points in non-dimensional terms. We provide some default systems, so Earth, Moon, Sun, Earth, Sun, Jupiter. I think those are relatively common, so those are provided by default, but you can create your own system if you like. And then we have dimensional EOM, so these are the equations of motion that use meters and seconds and so forth if you want to work directly in those. But the main usage is this EOM constructor. So this is a function which will return a function. It's going to return a function that can be accepted by solve IVP or IK45 or any of those other numerical integration schemes from SciPy. It takes in the mu of the system and also whether or not you want to integrate the state transition matrix, which is something we're going to cover in the next lecture. By default, that's false. Then we have an A matrix, and we do fxx and fyy and all that kind of stuff. The A matrix, I'll talk more about that in the next lecture. We've already seen it in the previous lecture from doing the linearization, but there's a different reason that it's here, and I'll talk about that in the next lecture. And then finally at the end, we have an equation for getting the initial velocity for a point. So that takes in an initial position, value for the Lagrange point, and the mu, and it returns xy velocity. So with that all out of the way, let's go ahead and get stuff plotting. So I'm going to say from CR3 BP, let's bring in Earth Moon as EM, we'll bring in the ELM constructor, and we'll also bring in the initial velocity. And we're also going to need solve IVP from SciPy, we'll need NumPy. We're also going to need matplotlib to plot the stuff. That should be it, I think. So let's start with some initial conditions. So let's first start by plotting an orbit that starts 100 meters away from the Lagrange point. So we're going to take em.L1, we're going to start with L1, and we're going to say plus 100 divided by em.L. So here I'm taking 100 meters and I'm non-dimensionalizing it. I'm going to put 0 for the rest of the values, the xyz position, the yz position, and the xyz velocity. Now I need the initial velocity, and for that I'm going to use this function, the initial velocity function, and I'm going to take a slice of IC. So when I take a 3 to 5 slice, this means use indices 3 and 4. So the x velocity and y velocity, we're just going to go ahead and set those directly. So let's do our initial velocity. So our initial position, let's give that the 0 and 1 slices of initial condition. For L point, it's em.L1, and mu, I think the cursor got a little screwed up there, em.mu, whoops, em.mu. So let's go ahead and run this real quick and make sure everything works kind of as expected. So if I look at IC, we see that there's no x velocity, but there is a y velocity. That's what we expect because we saw the equations for the initial velocity. The initial y velocity depends on the x position and only on the x position, and the initial x velocity depends only on the initial x velocity depends only on the y position. And so if we take this and we multiply this by em.conversion vector, it's showing us that our initial velocity is very small, so it's like 2 millimeters per second. So we're going quite slowly. Let's see. From here, we were going to want to use solve IVP to integrate these equations. Say trad, short for trajectory, equals solve. Oh, actually, first we need to get our ELMs, our equations of motion. So let's go ahead and throw that into the ELM constructor. So we need em.mu, and that's it. The STM is defaulted to false. We don't need the STM for now. So here we give it ELMs. We need to give it a t-span. So I'm going to integrate this for 2 weeks. So that's going to be 14 days times 24 hours per day times 3600 seconds per day divided by em.s to get us a non-dimensional value of time. Why not? That's our initial conditions. Method I'm going to leave is RK45. And then lastly, I'm going to fill in atol and rtol. So those are our absolute and relative tolerances. So an absolute tolerance is basically how precise do we want this to be. And I think a millimeter level of precision is probably good enough. Again, we need to non-dimensionalize it. This is basically saying that as it's deciding what time step to take, it's going to take the smallest time step such that doing RK4 versus RK5, the difference between them is within 1 millimeter. RTOL is relative precision, so that's like number of significant digits, and I don't really prefer that one because I want to know that everything's millimeter level accuracy. And with number of significant figures, it's a little awkward because our x position is kind of large. I mean, in non-dimensional terms, it's only one more significant digit, but I'd rather think about things in terms of millimeter level precision for everything instead of trying to think of like, okay, well, which value is this term going to have and how many significant figures and all that. So I'm going to set it to 0. Now SciPy is going to complain and it's going to force it to be 100 times machine epsilon, but that's fine because that's going to be really small, and ATOL is going to be rather larger than that. You can see that 0.001 divided by em.l. So that's 2e to the minus 12th, whereas our tol is going to get set to like e to the minus 14th, and then that's going to be multiplied by our values here. So our tol is going to end up really small, and whenever NumPy is integrating, basically whichever of these ends up being smaller gets ignored. So this should all be good. Let's run this to see if everything works correctly. Yep, like I said, rtol was set too low. So cool, let's go ahead and plot this. So now we can say ax.plot, and we'll do trajectory 0 all, trajectory 1 all, and trajectory 2 all. Oh, I think I need to say dot y, because this isn't just a trajectory, it also has time and a bunch of other factors in there. So let's see. Before we go further though, let's set the axes to be equal, because by default it just sort of picks whatever axes it likes, and we want this to actually be bounded by something. So I'm going to set my bound to be, I'm going to make it 400 meters, and I'm going to make x-axis bound to L1 minus bound up to, and then we're going to set y and z, and for some reason instead of being left and right, these are bottom and top. I don't know why, but so be it. And so let's take a look at that. So that's getting plotted in here. That looks like a nice little ellipse. That's looking pretty cool. Let's add the value of the Lagrange point. So I'm going to say em.L1, 0, 0, and we'll put it in black. And I'm also going to add the initial value for this guy. So I want to be able to see where this trajectory started. And we're going to make this, I'm going to make sure this is blue, and we're going to make this positive, or we're going to make it a plus sign. So let's do that. So that looks nice. So we start over here, and we're looping around, so this looks pretty good. But let's take a closer look at this. So I can't, this is just a picture, I can't rotate it. So I'm going to do this QT thing so that I get something I can interact with. And so let's take a look. I mean, it looks pretty solid. It looks like we're in a complete loop, but you can start to see here that there's some deviation. There's also some jaggedness, and that's because our tolerance, even at millimeter level precision, is fairly low actually, and the solver is able to take fairly large time steps. We can make it take smaller time steps by increasing our tolerance, but the thing I want to show you here is that if we zoom in real close, it's tough to zoom in this far without kind of like losing everything, but you can see that it's not everything is as it appears. So we're not actually quite on the same trajectory, and this isn't an artifact of how we've plotted this. This is because we're not actually on the same trajectory. We're not actually in a periodic thing, and you can see that more clearly if I increase the time up to, let's say, 4 weeks. Now you can see we fell off, right? We diverged from our oscillatory solution. So let's take a closer look at this, and let's add some more initial conditions. I want to take a look at we started at 100 meters away from the Lagrange point. I want to see what do things look at a little bit further. Let's say a kilometer away from the Lagrange point, or 10 kilometers. So to do that, I'm going to add a couple initial conditions, but first I'm going to take this IC, and I'm going to call this IC1, so that I can then create IC2 and 3. So we'll copy this, and here we'll replace IC1 with IC2, and here we'll replace it with 3. And so this one we're going to start 1,000 kilometers away, and this one 1,000 meters away, so 1 kilometer away from the Lagrange point. And this one is going to be 10 kilometers away from the Lagrange point. So let's also do our same replace trick here. We're going to replace this with traj1. And we'll copy this line, and we'll make it traj2 and traj3. So traj3, and then we'll copy these as well. And here we'll replace traj1 with traj2, and here we'll replace it with traj3, and we'll make the second one green and the last one red. Cool. So let's see what this looks like. Oh, one thing we need to change real quick is the bound. So since we're starting at 10 kilometers out, we'll probably want this to be, I don't know, 12 kilometers. Let's see. So, okay. So in all three cases, we see that everything's eventually falling off. And so what this is telling us is that we did our linear stability analysis, and we found that these conditions that we're exciting right now, they were purely imaginary in the linear system. And we said that we couldn't reach any conclusions about their stability for the nonlinear system, because we simply didn't know what those higher order terms were going to do. They could have pushed those center points left and made them stable. They could push them to the right, made them unstable, or they could have kept them as center points. And so here what we're seeing very definitively is that they are getting pushed to be unstable. They are getting pushed towards the right-hand side of the complex point. So anyway, let's zoom in and take a look. So the blue one we've already looked at. The green one, we can see that after one orbit, it's close to where it is, and if I zoom in, you'll see, as we saw with the blue one, that it's not quite in the same spot. So it's already getting off of its oscillatory trajectory. And then after only about a quarter of the way through the second orbit, we fall off and we go off very far towards the Earth. Earth is this way, since this way is decreasing x. And then we have the part where we start 10 kilometers away. So there we don't even really complete a full orbit. And one more thing I want to show here is I want to give a sense of scale. So I'm going to plot the moon on here as well. Let's give this a comment here. Plot L1. And let's plot the moon. So for that, we're going to need the lunar radius, because I want to actually plot it to scale. So let's take a quick look at that. So it's about 80 miles. What is that in kilometers? Here we go. It's about 1740 kilometers. So let's go ahead. 1740 kilometers, 123 for meters, divided by em.l, because we need to now dimensionalize it. And so we're going to do ax dot plot, and the moon is located at 1 minus em dot mu. And so I'm going to want to plot one point for negative the lunar radius, and we'll go ahead and we'll make this a blue plus sign, and one for positive lunar radius, so that we get a rough idea of where the moon is. So here we go. So if I zoom out, so there's the moon to scale. and the Earth is way over here, right? Because the Earth is at negative mu, and mu is about 0.012 in this case, so the Earth is way over here. So there's our moon to scale, and so you can see that starting near the Lagrange point, this is pretty small. So hopefully that gives you an interesting idea of sense of scale. So there's one more thing that I want to do in this lecture, and I want to come up with a sort of a crude station keeping algorithm. We want to stay on this trajectory, right? We want to stay near the Lagrange point, and we know that real missions need to do some kind of maneuvers to stay around there. So I want to come up with a simple one, and we're going to develop it a little bit further in the next lecture, but this one will just give us sort of a baseline and just kind of an idea. So what we're going to do is, as we integrate the trajectory, we're going to take a look at our position along this trajectory, and we're going to use this initial velocity function to figure out, okay, if we're at this point on the trajectory, if this is our current xy position, what does our velocity have to be on a trajectory that excites this oscillatory mode? And then we'll take a look at how that compares to the velocity that we actually have, and that'll allow us to compute a delta v, essentially. Now, we're going to allow that delta v to grow, so we're not just going to execute it anytime there's a difference, because we're going to assume that our thrusters don't have arbitrary precision. If the delta v is saying that I need to add 2 nanometers per second to my velocity, well, that's probably not very realistic. But I think something like a centimeter per second is realistic, and actually I can sort of prove that because we have some data from the Artemis probes, which you'll see in this paper, which is in the companion repo, and I don't have the code in there yet, but I will upload this file that I'm working on into this companion repo. But so there were these Artemis probes, which, long story short, they were Earth orbiting probes that were sent to the moon, and as part of their trajectory, they orbited the Lagrange points for a while, for about 3/4 of a year. And so here we have some information about station keeping they did. And so you can see that their maneuvers were as low as 1.17 centimeters per second. So we're going to use that as sort of a baseline, and we're going to allow our delta v to grow until it gets up to 1 centimeter per second, and then we'll execute a station keeping maneuver. And we're going to integrate for an entire year, and we're going to make our maximum step size 1 day, so that we have an opportunity to do a maneuver at least once a day. And then we'll sum up all of our maneuvers and we'll see how much delta v that cost. So to do that, we're going to need to break the integration up. Instead of doing things with solve IVP, we need to do our own step through it. So go down here, station keeping. So I'm going to do this for the 10,000, for the 10,000 meter case, the 10 kilometer case. So we'll go ahead and change these to IC4. And solver equals RK45. We pass it the same EOMs. Our T0 is 0, our Y0 is our IC. Our T-bound is 365 days times 24 hours per day times 3,600 seconds per hour divided by EM.S for non-dimensionalization, and we're going to give it the same, that's right, max step equals 24 times 3,600 divided by EM.S, and we'll have ATOL equals ATOL and RTOL equals 0. So that should work. This is going to give us an object that we can iterate through. So here we have to say while solver.status is running, we have to say solver.step, and actually first we need to set up a couple of arrays. So the nice thing about solve IVP is that it gives us a thing that has all the information we need, whereas when we step through it ourselves, we have to keep track of all that information ourselves. Let's see what's going on here. It doesn't like something. Undefined name IC. Oh, that's right, IC4. Okay. likewise for this guy. So I'm going to make a vector for all our delta v's. And each time we do a delta v, we're going to store it in the vector. We're going to store the magnitude in the vector so that at the end, we'll be able to compute how much delta v we spent and also how many maneuvers we had to do. And we'll compare those to the Artemis values. So we do solver.step, then we have to say y.append solver.y. And now we're going to check out what our velocity needs to be. So new velocity is going to be this initial velocity. The initial position is going to be solver.y, x and y value. L point is em.l1, and mu is em.mu. So now our delta v is going to be equal to our new velocity minus solver.y, and this is going to be our 3 to 5 slice because this is going to be our x and y velocity. And then we have dv norm. That's going to be np.norm dv. And so we're going to check if dv norm is greater than 1 centimeter. So we need to, or 1 centimeter per second. So we need to divide this by em.l and multiply it by em.s to get our non-dimensional value. I'm going to put a message in the console here, say we're burning. And we're going to take our all dv's and we're going to append dv norm. And we're going to take our state and we're going to set it equal to our new velocity. And finally, last but not least, I'd like to plot these. I want to make a new figure. And instead of traj1.y, it's just going to be y, but we have to do this little trick. And we'll need to transpose it so that we have the same sort of shape that we had earlier. So let's do a little find and replace here, and replace it with nothing. Okay, and we're going to want to plot L1 and set equal axes. Okay, so let's run this and see what happens. So there we go, we executed some maneuvers, and wow. So you can already see a couple of things happening here. So we stayed around the Lagrange point, which is cool. That's what we wanted to do. We wanted to stay around it, so we stayed around it for an entire year. We didn't quite stay around it in our initial trajectory. Like, we can see these rings here, so we're clearly we're falling off of our trajectory a little bit, and then we're catching ourselves as we do this delta v maneuver. So let's take a look at that all dv's vector, and I'm going to take the sum all dv's, and we need to, I think, multiply it by em.l and divide it by em.s to get a value in meters per second. So that tells us that we used a total of 0.5 meter per second of delta v. Now that sounds really good, but it's actually deceptive because we are in a circular restricted three-body problem. So we are not taking into account lunar eccentricity or solar gravity. Now, a long time before I made this video, I actually took this station-keeping algorithm and I put it in an ephemeris model. So if you're not aware of what an ephemeris model is, then all you need to know right now is that it takes into account lunar eccentricity and solar gravity. So the thing is, where this method starts to fall apart is the Lagrange point is moving. So the moon's orbit is eccentric, and so you're going around in your orbit, and then by the time you need to do a new burn, the Lagrange point has moved. And so you can recircularize, essentially, create a new circular restricted three-body problem and figure out where your Lagrange point is and where you are relative to it and what your velocity needs to be on a circular orbit around that Lagrange point. But when you do this constantly, you basically are just constantly trying to find some Lagrange point to be near. And the end result was that the station keeping algorithm in the ephemeris model, this station keeping algorithm, took hundreds of meters per second per year. And if we take a look again at the information from Artemis, what they did here in this table is they took the total, the cumulative delta V that they expended for station keeping. They excluded this one, which was the capture burn, and they included this one by accident, I think, because this maneuver in red, they had two probes here, and they actually moved one of them from L2 to L1. And I think I'm reading this correctly, which is to say that they used 3 centimeters per second of delta V to move the spacecraft all the way from L2, tens of thousands of kilometers past the moon, over to L1, tens of thousands of kilometers on the other side of the moon. But I digress. What they did here is they took the cumulative delta V used for station keeping, they divided it by the number of days they were in a Lissajous orbit, and they multiplied it by 365 to figure out how much would the average annualized cost of that station keeping be. So initially it was rather high, because these were just the initial maneuvers, but as they stayed in the orbit, you can see this average is going down. And it's still going down by the time they leave the halo orbit. I think, if I'm not mistaken, these guys ended up in lunar orbit. But so you can see that their average is getting to like 5 meters per second per year. So, and what's great about this is this is real data, right? This isn't simulated. They actually stayed in a halo orbit, or in a Lagrange point orbit, for 285 days. And this was trending downwards, so maybe it could have been even less. They expended 4 meters per second of delta V, so it's not going to get less than that, obviously, but it looks like it's asymptoting to somewhere between 4 and 5 meters per second per year. So that's something that we can expect. So going back here and to our lovely little station keeping here. We can't compare directly because we don't have an ephemeris model, but we will be developing this further in the next lecture, where we're going to take a look at a technique known as differential correction, where we're going to be able to write a different sort of station keeping algorithm, and it's actually going to be far better than this one. So I'd like to think that order of magnitude improvements in this sort of model will also lead to order of magnitude improvements in an ephemeris model. Building an ephemeris model is quite involved, and it's outside the scope of what I want to show here, so we're not going to end up building an ephemeris model, but we'll still build it in this model, and you'll get the ideas, and maybe you can play around with it on your own. One more thing before we go, I want to play around with the y values here. So I'm actually going to copy these initial conditions for the y and z values, just so we take a look at what they look like. And let's go ahead and do it for this guy as well. Why not? So when we do that, oops, I actually don't want to save this. Or I'll save it later. I do want to save it. It's running, it's burning. Okay, there's our station keeping. It looks pretty cool. It's got a nice little pattern. And here's our other ones. These look pretty much the same. So we saw that changing the y and changing the z, that didn't really do a whole lot. But there's one more thing that I wanted to note, and that's why these things are called halo orbits. So there's the moon back there, our semi-to-scale moon. And so you'll notice I can't really seem to get this to align quite properly, but when you're looking at the moon from Earth, so right now our camera is as if we were at Earth, and we're looking at it and we're looking at this orbit. So you can see this orbit is forming sort of a halo around the moon, and that's why these are called halo orbits. So hopefully you found this lecture useful or interesting. If you made it this far into the video, please leave a halo emoji in the comments. And thanks for watching, and I'll see you next time.